So here we are going to start the new topic, optimal control in modern control algorithms. Before we go to the main concept of the mathematical concept to derive the optimal control, let's work on the motivation, why we have to work on optimal control. So let me write some points here. The first point is multi-input, multi-input and multi-output system. So if you notice in this case, this we are handling the x dot equal to ax plus bu. So x can be vector, u also can be vector. So there are multiple states are involved in the system, also multiple control input. If you notice we use the command place, right? Place command. And by using the place command, we can place the poles to the desired location, right? But using this concept, this place concept, the way to place the poles in the desired location, can't fulfill all the design parameters. Cannot fulfill all the design parameters of the system objectives. This is very, very important because we are here actually limited number of them could be found on the closed loop pole locations. We can't capture all the design parameters in the control synthesis. Second problem is to determine the desired poles also very challenging. Which poles will give us the desired results? It is also very challenging to find the optimal poles which can fulfill the performance objectives. So this is also challenging. How to find the poles which can help us to come up the optimal results. So using the concept what we have designed for in the state feedback control, it is quite challenging, which can provide the optimal results. Another problem is another condition can be if there are many possibilities, if there are how to find the best possible solutions, how to find. So all these challenges can be achieved if you have the optimal control practice. The above challenges can be achieved by using the optimal control technique. So let us go how we can design optimal control. So optimal control, basically we are going to choose some objective function which will fulfill the design parameters, different design parameters in the system, which can take into picture, and also which can find the best solution out of many possibilities. So let's look a response of a second order system. For example, this is the desired values of the system and the response of the actual system. For example, this is something like this. So if you notice, after some time, the system goes to settle down after some time. So this is the desired values. And before its system goes to settle down, it goes through number of overshoot, undershoot, right? So these, before this goes to settle down, this part, for example, this is the time it goes to settle, and let's assume this is Ts. The time takes to settle down, Ts. And the time till Ts we call in control system, it is called transient response. Okay. Transient response. And after it settle down, the future time after Ts, it is called steady state condition. Right. But if you notice, the system till it goes to settle down, there's some transient energy in the system, and which is due to the overshoot, undershoot in the system. So if you want to reduce this overshoot, undershoot, and also if you want to achieve your system to reach faster to the steady state condition, then we need to apply some control. So it means that is two important part. There are two important component, which one is transient energy, another component is control energy. So we need to, using these two conditions, we need to find the objective function. That objective function will contain one component transient energy, another component control energy. So we have to balance between them so that we can get optimal result. And that optimal, once you go to the optimal condition, will come up best possible control. And that control basically nothing but the control gain matrix. And this objective function we defined by the cost function, which is can be defined as J equal to that objective function defined by 0 to infinity x transpose qx plus u transpose r u and dt. From this equation, we can see that the control energy and transient energy with respect to time been defined. Therefore, the objective function of the optimal control problem must be time integral. So that's why we have taken time integral here. Must be time integral. Yeah. Of the sum of the transient energy, and this is the control energy. So now, our main aim is how we can minimize this function while the system overshoot and undershoot can be maintained and minimized, and we can reach to the desired position very quickly. Now let us define what are the parameters in equation 1. So here J is the performance index. Or sometimes we call cost function, which is always positive. It's positive. And x is the state vector, state, and u is the control input, and q is the symmetric positive semi-definite matrix. Semi-definite. Symmetry matrix means the determinant of the matrix can be 0 or greater than 0. It can be negative. And R, symmetric positive so here, if you notice here, we have two important conditions for this equation one. If Q is greater than R, we can get faster convergence of X, which is supposed to go to 0, but we need to apply more control effort. So it means U is large. And if R greater than Q, then convergence can be slower, slow convergence of X tends to 0, and U is small. So it is obvious if you apply more control input, if you put more energy in the system, you can get to the desired value fast. And if you apply more less energy, you will reach to the desired location or position not very fast. Now we'll come up with the mathematical formulation of this, and before that also let me define some important terminology. This process sometimes we call linear quadratic regulator problem. The above process of designing control is called linear quadratic regulator problem. So what does mean linear? Linear means we are working on the linear system. Quadratic basically here, the cost is J's are function of quadratic form because these are quadratic form. That's why it is quadratic. And regulator, basically we are designing the controller, right? A regulator. That's why it is called linear quadratic regulator problem. Now we are going to introduce, so now we are going to do the mathematical problem before that. Let me write mathematical analysis. So for that, let us introduce a new matrix. Let's introduce a symmetric matrix. P, so we satisfy the condition P transpose equal to P. And if you modify equation 1, now if you modify and modifying equation 1 as J equal to X naught transpose p x naught plus, sorry, minus x naught transpose p x naught plus we are taking the integral 0 to infinity x transpose u x plus u transpose r u dt. Okay. So here we have introduced this term plus minus. So that's nominally. So here basically x naught is the initial state. So if we introduce this term, this our j first function say, further j can be written as x naught transpose p x naught plus 0 to infinity, we can write d dt x transpose px plus x transpose qx plus u transpose ru dt. Okay. So let us look how we can write this expression in this, because previously we had this expression and how we are getting this. So let me explain on this. So here we can simplify 0 to infinity d dt x transpose px term. So you can write this term as x transpose px 0 to infinity. And if you take integral from infinity to 0, so we can write x transpose px infinity minus x transpose px 0. If you notice carefully, as if once it is goes to, because you can write this term goes to 0 as t tends to infinity, right? So in that condition, we can write this term we can write as, this term goes to 0 as x tends to 0 as t tends to infinity. So we can write from this, we can write 0 minus x naught transpose p x naught, or we can write minus x naught transpose p x naught. So I hope it is clear. So now we are getting this expression, the value of this expression, nothing but minus x naught transpose p x naught, which is we have added here. So I hope it is clear. Now again, let's find the derivative of x transpose px. So from this we can write x dot t px plus x transpose p x dot. So here we can write, in place of x dot, we can write our state equation ax plus bu transpose px plus x transpose p. In place of x dot, we can write ax plus bu. Right. Now we can also write z equal to x naught. So this is equation number, for example, 2. Let us define this equation number 2. And let's go back to again the j, first function j. What you have, x naught transpose p x naught plus 0 to infinity. So in place of this term, we can express this whole term. Let us look how we can write ax plus bu transpose px plus x transpose p ax plus du. This is the first term we are getting for this expression, and we'll have the remaining term plus x transpose q x plus u transpose r u dt. Okay. Now let's simplify this whole expression. So here we can write x plus bu transpose px plus x transpose p ax plus ax plus bu we can write as x transpose a transpose, because we know that x ax transpose we can write x transpose a transpose, right? This you know. So we can write plus u transpose b transpose px plus x transpose PAX plus x transpose PBU. And from this we can further write x transpose A transpose PX plus Q transpose B transpose PX plus x transpose PA x plus x transpose PBU. We can write. And from this we can write, we can take, so we can use this, the PA, the term here, and A transpose P. From these two terms we can write x transpose, we can take common, and we can write AT P plus PA, and we can write the remaining terms U transpose B transpose PX plus X transpose PBU, right? And now we can use this term in equation 3, in equation 2 we can substitute. So now the first function j equal to, we can write x naught transpose px naught plus 0 to infinity x transpose A transpose P plus PA, sorry, plus Q, we can write also, because for the second terms we can write this part, I can take the common, plus Q into X plus U transpose RU plus X transpose P BU plus U transpose B transpose PX into dt, right? So here we'll further simplify this expression here. So let's work on the last three terms. Let's work on the last three terms. We want to simplify this expression. It is somehow it is in the closed form, but it is not the second this term. So let's work on how we can further simplify this expression. Okay, let us define this term as term one. So term one we can write as U transpose RU plus U transpose, this is U, right? This is U transpose B transpose PX plus X transpose PB. We can write as U transpose. We are adding some term here to make the thing simple. Plus U transpose B transpose PX plus X transpose PB U as it is. So we are adding one term X transpose PB R inverse B transpose PX and minus X transpose same term PB R inverse B transpose PX. Okay. And from this, we can further simplify. We can simplify U transpose plus X transpose P R inverse into RU plus B transpose PX minus X transpose PB R inverse B transpose PX. Or we can write this expression as, the first expression as U plus R inverse B transpose PX whole transpose R into U plus, we can write R inverse B transpose PX. Yeah, we can write, and minus the same term X transpose PB R inverse B transpose PX. So this is the form we are getting from our last term plus three terms, right? So what we'll do is we'll substitute this whole term in equation 4, so equation 5, in J, in corresponds and J, equation 6. So let's substitute six in equation 5. So we are getting J equal to X naught transpose Px naught plus 0 to infinity X transpose A transpose P plus PA plus Q into X plus U plus R inverse B transpose PX transpose R U plus R inverse B transpose PX and minus X transpose the last term of equation 6 PB R inverse B transpose P into X. This is terminal. And again, we can further simplify the expression as equal to X naught T. We are very close to the final solution very soon. Px naught plus 0 to infinity X transpose A transpose P plus P plus Q minus PB R inverse B transpose P into X. And we have another term U plus R inverse B transpose Px transpose into Ru plus R inverse P B transpose Px dt. So if you notice here, uh, there are two important terms in this equation. Say, from the last equation, last term, please note carefully. From the last term of this equation, this is the last term, right? This term, how we can make 0? If you make this equal to 0, right? From the last term, we easily can write. So here, if you select U equal to minus R inverse B transpose Px, yeah, if you select from this term, in this term, if you select U equal to minus the other, if you take U equal to minus this term, then whole term goes to 0, right? So you can write something like this. For example, so if you select this, the term 2 goes to 0. And already you know from the from our last lectures in the state feedback control, already we know U equal to minus Kx, right? Full state feedback control concept is already have done. So now if you compare both this equation, now let us define this equation number 7 and this is equation 8. Comparing equations 7 and 8, we have A equal to R inverse B transpose P. Wow. We have found very, very important relation for the control K. So this is very, very important relation. So here, if you notice here in this equation, we are guessing some value R. P is given to us. So R already as a different matrix and P is some matrix, semi-different matrix we have to choose, right? So here, you can write here, P is symmetric matrix. But here, if you notice, we don't have, we need to find the P matrix. We don't have the expression for P. So this P we can find if you solve this expression. Okay. Because here, what you are given, so Q is given, Q we choose some matrix. So here Q already we choose symmetric positive different matrix, some matrix, and also R, also symmetric positive different matrix. But only in this expression, in equation 8, in equation 8, 9, the only unknown is P. So P now we have to find. So this P we can find from this term 1. If you denote this term 1, this is, let us resume, this is, so from term 1 we can write. So what is the condition again? We can assume if we can make the inside part, the inside, if we can make, if you consider this term to be 0, then we can say J can be minimized, because already we came up this condition by assuming this condition to 0. So term 2 can be minimized if you consider this thing. Again, if you consider this term equal to 0, then we can indirectly say J can be minimized, because both the terms inside the bracket is goes to 0. So now we can write if A transpose P plus PA plus Q minus PB R inverse B transpose P equal to 0, then first term for term 1 it goes to 0. And hence J is minimized. That is our main goal, how to minimize the J, minimized. So from this we can write A transpose P plus PA plus Q minus PB R inverse P transpose P equal to 0. This is another important condition we have now. This is another condition we are having. And let us define this as equation number 10. So by using equation 9 and 10, we can design optimal control or linear quadratic regulator, LQR problem. This equation sometimes also we say algebraic Riccati equation. So if you solve 10 to find P, and this P goes to equation 9 to find A, and this K goes to U equal to minus Kx. So this is how we can design optimal control U. So if you notice, we started with J and we had some mathematical manipulation, and we have two conditions, condition 9 and 10. These are the optimal conditions which can make the cost function J to be minimized, this J. So that's why we call optimal problem, because we are minimizing some function to get optimal result of a problem. This is very powerful technique in for designing the control algorithm for dynamical system. And we'll take an example because today's time is short. We'll take an example how we can implement this LQR control. This is also we call LQR control, linear quadratic regulator control. So we'll how we can use this concept for a problem will come up in the next lecture. Thank you.